All right, so now it should be recording, I hope, and we'll see how it goes. So the idea would be start there and forget about it. So let me sign in as usual. And I do want to review these two concepts, two things before I go for the general review. I want to review those separately. All right, let me start audio recording this as well. Let's see what's working better. All right. So the two concepts that I want to talk about is how can you see a flux integral, whether this flux integral is positive or negative. All right. We already know how to do this for a work integral in 2D, in 2 dimensions, right? We know, for example, that if we have a vector field that looks like, I'm going to draw it in a second. All right, if I have a vector field that looks like this, perhaps. Vector field that looks like this. There's vectors right here. They go like this. They're short over here. Here's the y-axis, the x-axis goes like this. They get longer as you go over to the x, as the x gets bigger. Gets longer like this. So such a vector field, for example, would be the vector field that they would do this, for example, would be f. It always goes one to the right, but the further you are over here, the more to the right it goes, the longer it is. This would be, for example, a vector field x, comma 0. Would look like this. All right. And let's make this x, comma 0. Let's pretend this is a 3-dimensional vector field for now. But first of all, let's look at the work integration. If I do work integral along this path here, this is the curve C1. Integral over C1 of f dr is what? Positive or negative? Positive, because you're going with the flow. It's very easy to do. You're getting pushed along, so you're getting energy back. So you're getting work back. How about if I do this thing as a flux integral? For the flux integration here, I need to have this. I need to have a 3-dimensional vector field here. And I want to imagine this as coming out here. And all these vectors are pointing in the same direction, just in 3 dimensions. And now I'm going to so imagine this extending in the z direction like this. Like this. So imagine this as a 3D vector field. And let's put a slice in here like this. So let's say I put a surface in like this, which of course is a 3D surface. It's like a sheet of paper like this, really, in 3 dimensions, if you will, like this. Can you imagine it? So I'm putting in a sheet of paper like this. What is the flux to this surface, positive or negative? So I want to know what is let's call this surface S1. I want to know the integral of the flux of this vector field like this. This is the flux integration. Remember that? Is it positive or negative? Well, how can you tell? The idea would be, you know what, this is supposed to be the normal vector. So where's the normal vector to this plane? It's pointing this way, right? It could point this way or this way. I'm not sure about the orientation of this surface. So it could point this way or that way. So let's make it point this way. Let's say the normal vector points this way here. Let's say the surface is oriented like this. And then it points this way here. So the normal vector dot this f, dot this vector field is what has what sign? vector f dot n is what? Positive, because it's a dot product. Remember, how do you tell that it's positive? But the dot product gives you basically the cosine of the angle, right? Cosine of the angle is 0 here, so that's cosine of 0 is 1 is positive, so that means it's positive. It's basically the cosine of the angle between them. Positive for S1. So that means that this integration comes out positive. Got it? If I take a surface like this, though, if I take another surface and embed it in here like this, perhaps, let's say I take this surface here, again, 3D surface here, S2, then what happens now? The normal vector of this surface here, depending, could be up or down like this, or maybe going down like this, depending on the orientation of the surface. Let's say it goes up. Now what's the flux of this vector field to the surface S2? What is the flux of f dot n ds to this surface S2? Now it's going to be what? Well, what about those vectors n and f? What is f dot n here in this case? 0, because the two vectors are perpendicular, right? So it's going to be 0. Means that the flux is going to be about 0. Does this make sense? Yes, that makes sense, because nothing flows. If you think of this as a sheet of paper, this is very thin. Nothing flows through the sheet. It's too thin for it. Everything goes past it, basically. Whereas here, it absorbs the full force of the flow, so everything goes through it, so this is a positive one. If the surface is oriented this way or this way, then it will be negative. Got it? And by the similar token, I can look at this, look for sinks at sources. So I could look up a vector field like this. Let's say I have another vector field that looks again like the one before, like the one I just drew. So it looks like small arrows over here, bigger arrows, and yet bigger arrows. I want to find out what happens at this point P here. Is it what they call a sink, or is it what they call a source? So the way to figure this out, so is P a sink or a source? Sink or a source. So the way to figure this out is you take a small cube or a small test surface. Did you imagine it? And you insert this into the flow here, into this vector field, like this. A small box Q. And you want to find out the entire flux through this surface Q ds. Is it positive or negative? Well, what do you think? It's positive. Why is it positive? That's right, because on this side here, there's short vectors coming in, but on this side, the vectors that go out are bigger.
So do you not include the first small vector?
Say it again?
You don't include the smaller vectors before them?
You do. Think of it in the abstract. Vectors that come in here, are they smaller or larger than the vectors that come here? The vectors, they go small, bigger, and then bigger as you go along this side. The vectors so the stuff that comes in here is perhaps this big. I'm not sure, perhaps this big here. But the thing that goes out is bigger, because as you go more to the right, the vectors get bigger, right? In this case, more comes out than comes in. That means there's a net positive in there, and therefore you would say that this is positive. So you would call P a sink or a source. This source, exactly. And also this is one way to tell what the divergence of a vector field means. Because another way, what this is equal to, if this is a closed surface, if Q is closed, what can I say? If Q is closed, then the double integral over the Q surface F dot n ds is equal to what by what theorem? Triple integral over what? Over the interior of Q, over the inside of Q, of what? Divergence of the vector field F, dv, right? So in this case, you can see that you can figure out the triple integral of the divergent geometrically as well. We're interpreting it like this, and then seeing whether it's sink or source. So in this case, this would be the divergence would be positive. Got it? Yeah.
And if you had drawn this where the longer arrows were first and then it went shorter, it would be negative because it would be coming in longer and then going out shorter.
Right. Right.
So
Or,
if it's a source, it's always positive divergence.
yeah, that's right. So another way to look, another much more simple vector field would be this vector field here. And the point in between, this point P, is the sink or source. In this case, P is clearly what? A sink or source. Does stuff disappear there, or does stuff come from it? Clearly stuff disappears there. It's a sink, right? It's clearly P is a sink. And what is this vector field here, by the way? What's this? Can you tell me a natural phenomenon that has this vector field? You're standing on it. The Earth, the gravity, right? A gravity field. So gravity, this is the source of the sink here. This is where everything gravitates towards, and that's the sink, right? And other way around, you could have a vector field like this. This is the vector field. F is the vector field minus x minus y here. This would be this one. Or you could have a vector field like this. And I have my point P here. And I might want to know what is the I might want to know what is the triple integral of the divergence of this vector field F dv, positive or negative in this case. What is it? It's positive, right? Because you do the same thing. You place a little bubble around here, and then everything comes out of it. Nothing goes in at all. So this is positive for sure, right? Therefore, this flux is positive, so that means the divergence is positive as well. This is going to be positive. And in fact, this is a vector field. This vector field here is, for example, F is equal to x, y, z is that vector field. X, y, z is a vector field that looks like this. Everything goes away. And what is the divergence of x, y, z? If the vector field is x, y, z, what's the divergence of this? What's the divergence of vector field x, y, z? It's the first component with the x derivative, the second component with the y derivative, the third component with the z derivative, which is what? 1 plus 1 plus 1. You add them up for the divergence, that comes out 3. So indeed, that the triple integral of 3 of this dv is definitely positive. Whereas the divergence of this one comes out to be negative, because it's negative 3. Got it? So you can see all these things visually as well, at least in some special cases when I'm drawing this. These are my favorite types of questions, so you will get all these geometric questions. Find the sign of this guy here, which means the same thing. You have to convert to a flux integration. Find the sign of a work along a path, which we did before. So all of this is going to be on the exam. All right. So by the way, I should put a z here just in case. All right. Very good. Now as for the exam review, so So let's see what we have here. I did post the practice exam with the answers this time, right? I hope you got the answers. I hope you looked through them. Many of the answers are just the answers. I didn't tell you how I got it, so maybe there's some questions about it. So let's take a look at the exam first of all. So the exam will go as usual. The first question is a question about definitions. Define something. Maybe any of these things is fair game here. What's the definition of it? You can have a cheat sheet again, so this is going to be an automatic bonus point. I mean, if you don't get this right, that's your own fault. So you just write these things down on your cheat sheet carefully if you don't remember them, and then that'll be that. Second question is true-false questions. Third question is some picture problems. So these are picture problems here, for example. I might ask who is who. Do you have any questions about that? Can you do that? Is it all clear why these guys come out the way they come out? This one is which one? Well, you do the easy one first. This one is everything goes away from it. Away from it. By the way, is the divergence of this positive or negative? Positive, very good. The divergence of this will be positive, right? Very good. Okay, good. And so, which one is this guy here? This is 1. The one that has a minus yx is a little confusing, so let's postpone this. Let's go for the obvious ones. The obvious one has a 1 here, means everything goes up. It could go up like this, or like this, or like this, but nothing can go down. Vectors could go up like this. They could have a large x, a negative component, but so which one is this one? This guy here, obviously. And this one, everybody goes to the right. They could go to the right like this, or like this, or like this if they want to, but they all go to the right. It's going to be this one, and then this one is left over. This one is left over for 2. Right. Which of these integrals are, which of these vector fields, of these 2 vector fields are not conservative? Yeah, the left one, right? Why? Because if you have a conservative vector field, you have by various theorems that we did, you know that the integral over every closed curve is going to be 0. Here you put a closed curve like this, then it would be positive, or like this, it would be negative. Either way, it would not be 0, the integral over these closed curves, so this can't be conservative. Here it's hard to say, so I guess this is clearly not conservative. This may or may not be conservative, it's hard to say, but you could try and argue that no matter what closed curve you draw here, you have places on the closed curve where you gain work and where you have to expend work, and it kind of averages out. So you could see that this might be 0 conceivably. Then I want to integrate from 0 minus 1 to 1, 0. 0 minus 1 is right here. 0 minus 1 to 1, 0. I want to go this way. Positive or negative? Positive, exactly. And if I go from minus 2 minus 1 to 2 minus 1, from minus 2 minus 1 minus 2, let's do this one, minus 2, 1. This will be this guy here, positive or negative? Negative, very good, nice. Okay, very good. And similarly for these surface integrations, these flux integrations, what's the first one? Positive or negative? Flux to this surface S, imagining it as a 3D surface. What's the flux of this? Positive. The second case has flux 0, and the third one has flux negative, right? Because there's an obtuse angle here, so an obtuse angle here between these vectors and this normal vector, so therefore is a sine, cosine of it is negative, so that there you go. True or false? If the divergence of a vector field is 0, the vector field is conservative. True or false? False. What is true that is that who has to be 0 for it to be conservative? The curl. The curl, right? So in fact, the next question is right. If the vector field f is conservative, then the curl of f is equal to 0. And this goes under certain conditions, goes the other way around as well. Not always, but usually. See if a line integral is independent of the path, then the double integral of f dot n, the ds is equal to 0 for every path surface S. True or false? It doesn't even make any sense, right? Path surface, what the heck is that? So this is definitely false. What is true though is the next one, that is saying if a vector field is conservative, then the integral of f dr is equal to 0 for every closed path C. This only applies to vector fields. So this is not a vector field, so this doesn't make any sense. With vector fields. Fundamental theorem applies to vector fields. What does it say? What does it say, the fundamental theorem of line integrations? While we're at it? Right, exactly. So if the vector field is conservative, then the work of FDR over some curve C is equal to the potential function at the endpoint minus the potential function at the beginning point of the curve C. And since you need a vector field, this doesn't make any sense. Can you apply the fundamental theorem of line integrals for this vector field here? What do you have to check? It's a vector field, so you need to check what? Is it conservative? If so, then it applies, and this is conservative because the x derivative of this is going to be 12xy, and the y derivative of this is going to be 12xy, so this is conservative, yes. True. Can you apply Green's theorem for a curve C, which is a straight line from 0, 0, 0 to 1, 2, 3, yes or no? For two reasons, for several reasons. Why? What are some reasons for this? Closed curve, and it has to be also a curve where? In R2, an R2 curve. So this doesn't work because it's a three-dimensional curve. What's the three-dimensional equivalent of Green's theorem called? Not Gauss, but Stokes theorem. So, could you apply Stokes theorem to this one here? No, because what you need for Stokes theorem is you have to have a closed curve C. It is bounding some surface on top of it, but it's got to be a closed curve for sure. Can you apply Green's theorem for the vector field, for this vector field and a closed surface S? No, because Green's theorem doesn't apply for closed surfaces, it applies for closed curves. And only this, and this would have to be conservative, which it probably isn't, I don't know. Can you apply the Gauss theorem for this thing and the surface given by z is equal to f of xy? Gauss theorem says that, what does Gauss theorem say again? That's right, and it works for what kind of surface? It's a triple integral over some volume, so it's got to be some volume, right? So the surface that you have has to be closed, has to enclose a surface, has to enclose a volume. So Gauss theorem applies only for closed surface. This surface is not closed. The surface given to you by z is equal to f of x is never closed because it never passes the horizontal line test, the vertical line test. So it can never be a function. Stokes theorem for the 3D vector field and the surface S given by this, does this work there? Well, that depends. It depends. It could work out if it so happens that the curve is the boundary of the surface S and is a closed curve, then yes, you could apply Stokes theorem. If not, you cannot. This is a dumb question you can't answer. This is not a true-false question. This is a maybe question. Okay, very good. So then I guess the curl and the divergence, you can do those, right? I'm sure you can handle that. Okay, should we find a potential function just in case? Let's practice that. Who remembers which one of these was conservative? Let's look at a 3D vector field. For example, the G and H, were they true or false? Were they conservative? Does anybody remember? They were not, but both of them were not. How do I find out? How do I find out if a vector field is conservative? I compute what? Right, but if it's a 3D vector field, then what do I do? Find the curl, that's right. So if the curl was 0, it would be conservative. If the curl was not 0, it would not be conservative. In this case, I think D works. D works, I think. So let's try to do number D and make sure that we can work this out. So number D says the vector field is 2xy, x squared plus z squared 2y, zy. So my vector field is I have a vector field F. I forgot already. 2, what is it? 2xy.
X squared plus z squared. 2z.
So I want to find out if it's conservative, and whether, and after that I want to find out how to find the potential function, right? Now remember, in your exam you may use Maple, right, or Wolfram Alpha. So what's the easiest way to check whether this is conservative? Find the curl with Wolfram Alpha, right? Everybody know that? That's right. So this is it can't get any easier than that. Simply type in curl. You best put this in curly brackets, although it does work. It does work in multiple in different varieties of brackets as well. So curly brackets work the best. It was equal to 2xy comma x squared plus z squared comma 2zy. Let's hit it. Curl comes out to be 0, so yes, this is conservative, so now I have to find the potential function. So it's conservative. So that means I want to find the potential function. That means I want to look for a function f such that the fx derivative is equal to what? The fx derivative is going to be equal to the first component. Potential function means that the function, it's a function, not a vector field, but a function, whose x derivative is equal to this. And therefore, the function f is the integral of this with respect to x, which means what? Plus a function that could depend on y and z. All right, so that's it. Then you take the y derivative of this. The y derivative of this is going to be equal to x squared plus the y derivative of c, and I want this to be equal to what? I want this to be equal to x squared plus z squared. The x's drop out, no coincidence, the x's have to drop out here, no more x's left here. But now you know that cy, the y derivative of c is equal to z squared. So therefore, c is equal to what? yz squared. Not exactly it. It could be a plus of plus what? Plus a function of z only, right? Okay, so far I have that f is right now equal to x squared y plus yz squared plus d of z. Putting this in here. So that means I take the derivative again. This time the z derivative. The z derivative of this function that I have written up so far is going to be, the first guy goes away, it's 2zy plus the d prime, or the dz derivative, if you will. It's going to be equal to 2zy, so that means that this cancels out, no coincidence. It has to happen that the y's cancel out. That everything cancels out is just a lucky coincidence, but it doesn't have to be, that at least the y's have to go away. There could be z's left, but now you know that there are no z's left, so you know that the d is equal to what? D is equal to a constant. So that means that this is your potential function. Okay, got it? So potential function, fairly easy to do. A 3D function, when we first did this, looked very confusing. By this time, it should be actually very easy. And hopefully you wonder why you ever thought this was complicated. I hope. Okay, very nice. Now let's go for some more interesting questions. Some interesting questions. All right. For what? How would you do this now? For what? For what? You have an x or y to put here. What do you put here? What is the outer integration? The outer integration should be the x, right? Because the outer integration goes from x, from 0, this is 0, this is 1 here in this case. I didn't write this in here. So you would say for y goes from something to something, and x goes from 0 to 1, and y goes from where to where? 1 minus x. And if you type this in, hit enter, it pops up the answer. And as long as I see this picture, I believe you that you did this, that you did this by yourself. But without this picture, I would not believe it. Kind of.
And it would be dy dx.
Say it again. Yes. So the integral would be the integral dy dx. That means the first one goes, the first bound that you want to put in here is the y, but the way you want to think of it is to first fix the outermost. Yeah. So you first fix an x between two numbers. Based on this x, you fix the y. Yeah. No, just integrate. Integrate will be fine. All right. Integrate would work fine. Another place that would be, so that would be kind of hard. So B, for example, is a piece of cake. B, you just type it in and get it over with. I won't even ask that in the exam probably. It's too easy at this stage. C, D, and E, and F, and G, and H, and I, you can do this by typing it in straightforward. All of those. The reason being is, you know all the curves here, you know everything. You know all the curves here, so you know what you have to type in at what point, the d or the derivatives or whatever, the x to y's, the dx, the dy's, whatever. Just plug everything at the right place, write in Wolfram alpha, and you get the answer. Now, the last two are a little tricky here. Find this surface integral and this surface integral here, because you have to draw the surface S here. Except for in this case, this is easy again. Why can you do this straight out here? Because they tell you where the x and the y go, right? They tell you that the x and the y are limited between 0 and 2 and 0 and 4 respectively, right? So therefore you can type this into Wolfram alpha right away again. Let's do this. How would this number j look like? J in Wolfram alpha would look like this. J is x minus 2y plus z. Double integral, I guess, was it? Double integral SDS. So z is equal to 10 minus 2x plus 2y. Right? So what I want to see, at least there, what I want to see is I want to see the fx here. The fy, what's the fx? What's the fy? And the rest is, you can plug in the rest by using Wolfram alpha. You don't even have to draw a picture because they say that x goes between 0 and 2 and the y goes between 0 and 4, whatever they say. Okay, so therefore you can type this into Wolfram alpha straight up. You type in the integrate. The function to integrate is x minus 2y plus, but you don't type in the z, but because what do you type in? What's the type in here? 10 minus 2x plus 2y. All right, that's it. You put brackets around, don't forget that. You put brackets around here. Because the ds is equal to what? The ds is equal to the square root of and the square root of what? It is 1 plus the fx squared, but the fx is what? Is minus 2, so the fx squared is what? 4 plus the fy squared, which is another 4. So there. And now comes the, do you know the bounds? Well, in this case, you know the bounds easily because they say x goes from 0 to 2 and y goes from 0 to 4. So you say 4y equals 0 to 4 and x equals 0 to 2. You hit enter, hope for the best, keep your fingers crossed, and you see if you got the right answer, and voila. There we go. 216. Who would have thought? Got it? Now, of course, you could basically do this in your head also, but this is okay. You don't have to. Another, the one where you really have to do some work here is again this one here. The number k. K is much more tricky. Because for k, I have to see the picture here. The tricky part is, what is the z? It goes the same way as this. You got to find out the z, the f of x, z is equal to f of xy. Find the fx, find the fy, find the square root of that 1 plus fx squared plus fy squared and all of that. But you don't know where the x's and y's come from. So that means you have to draw this. So what I want to see in this case here is, S is the first octant portion of the cylinder y squared plus z squared is equal to 9, which is what? Y squared plus z squared is equal to 9, which is a circle in the xy, in the xz, in the zy plane. In the zy plane, so this would be like this circle here. And it would be in the first octant only, so this part of the circle is it. Like this. You extend this circle between x goes from 0 to 4, so here's 4, so that means you have another circle right here. This is it. All right? Now you're in business. Now you can find out what is the surface. The surface that you're talking about is this part here. Which is given by what? Z is equal to f of xy, but what's the f of xy in my case? Well, I know that this is going to be, this was coming from the z squared plus y squared is equal to what? 9. So based on that, how can I derive this in the form z is equal to? Right, I take the plus or minus square, but this is the top part of this part only, so this is this plus squared only, so the z is equal to the square root of 9 minus x minus y squared, right? Then you should find out the fx and the fy separately. You should do this in your head. The fx is this 1 over the square root of this. This gives you the square root of 9 minus y squared at the bottom. Half comes out, but the half gets cancelled against the 2y, and there's a y is a minus, like this. I'm sorry, this is the fy. What's the fx? Stupid. Fx is 0. Fx is fy is 0. And now you're in business. What does the x? So you set up this integration by saying the w. You figure out the dA as Usually, what you usually want to try is the dy and the dx. Does this work in this case? Yes, because the x goes from where to where? From 0 to 4, actually, because this is the 4 here. This is the x. This is the y. So the outer one is the x, so it's from 0 to 4. And what does the y do? Pick one of these x's here, like this one. The y simply goes from here to where? Here, what's this? How far out is this? 3, right? 3. Because this is a circle of radius 3. This is a circle of radius 3. Got it? And now you have all the ingredients to type it into Wolfram alpha again, except for the function that you put in here, of course, would be the function that we put in here is x plus z. So this would be x plus z, but z is what? Is equal to, is equal to square root of 9 minus y squared is the function f. Here we go, is z. Don't forget brackets around here and you're in business. Okay, so from this, if you write this down and then after that give me the answer, I'm happy. But I do want to see, if you don't draw this, I don't believe that you did this right, only by yourself. And I doubt that you can do this in your head. I mean, maybe you could, maybe you're a math genius and you could do it in your head, but I doubt it. So, no offense.
Where did you get the negative y over square root of 9 minus x squared?
This one is this one here?
Yeah.
The fy, the y derivative of this.
Oh, okay.
By the chain, this is power 1/2. The half comes down, gives you 1/2 times 9 minus y squared to the minus 1/2, which is y squared on the bottom. Minus 1/2, 1/2 goes in front. Times the inner derivative, the inner derivative is minus 2y. 2's cancel out, I'm left with the minus. Okay. So there will be a couple of these places that you can solve pretty nicely with Wolfram alpha, but you have to maybe draw some picture of the domain and of the x and y's. You may have to do that. And then there's going to be a whole bunch of other problems which you have to do by applying some theorem. Maybe after you apply this theorem, you still have to do some integration. Maybe sometimes you do, sometimes you don't. So in this case, so number 7, there's shortcuts here, because they all involve, as you know, they all involve vector fields, vector field integration here. In fact, number 7, the only theorem that applies there is they're all two-dimensional vector fields. So your choices are either, except for part B, your choices are either to do it, figure out what the x is of t, what the y is of t, what the dx is, what the dy is, plug it all in, and use Wolfram alpha to figure it out. The other choice is fundamental theorem of line integration if it's a conservative vector field and not a closed curve. And if it's a closed curve, then you use what theorem without thinking? Green's theorem. Maybe that gets you. Maybe you lucked out. Okay. So now, do you want me to do one of these things here? Are you good with any of them? Are you good with all of them? Let's focus on. Let's zoom in on C perhaps. FDR, where F is this guy here, C is the upper half of the circle from 1 to minus 1. Okay, what are you trying to do here? What are your choices? Green's theorem a possibility? Is Green's theorem a possibility? So say no. No, very good, right, exactly. So not a possibility because why not? It's a half circle, it's not a closed curve. So half circles don't work for Green's theorem, so it doesn't work. Then you say, well, this is too bad, because this means I have to work out the integral of y squared plus 1 dx, dx y squared plus 1 dy. This is a pain in the butt because the x and the y's are sines and cosines, so it's going to be ugly. Not too bad, since you could type this into Wolfram alpha just fine. It would not be so ugly, but it's still a lot of typing. Is there a better way to do this? Yes, because what could you use here if it did apply? What could you use here? Which one? Find the potential function, that's right. So does this have a potential function? What's the x derivative of this one here? And the y derivative of this one? So it has a potential function, right? And for two-dimensional vector fields, you can often guess it. So let's try and guess it. So I want to guess, so the guessing, it goes like this. I simply, I want to have y to the third plus 1 is the fx. But then the f must be what? X times y to the third plus, how do you get a 1 here? Plus x, right? And so this is your guess. You try to see if that's going to do it. Is this going to do it? What do I mean by saying is this going to do it? Take the y derivative. The y derivative, this gives me 3xy squared. But that's not exactly right. I'm lucky I get the 3xy squared, but I get a plus 1 here. So how do I get a plus 1 from a y derivative? By having a single y in the original function, right? That means the original function's got to be plus y here. There you go. That's your potential function. So now you can do this in your head. The answer of this would be x y to the third plus x plus y from minus 1, 0 to 1, 0. Y is 0, so this gives you 0, 0, and this gives you 1 minus minus 1. Got it? Okay, so these all of these work in similar way. You can almost always do them in your head. Then there will be things that are more complicated than Green's theorem, where I mix up. I have line integrations, I have flux integrals, I have divergence integrations, I have triple integrals perhaps. Anything goes. This would be this block here. Any ones you want me to do? Let's look at this one here. Flux integration, so what do you keep in mind? You might be able to use what theorem? Gauss's theorem. It applies if the surface is what? The surface is a closed surface, right? Is this a closed surface here? Yes, because this is sphere radius 2, right? So this means that Gauss theorem applies here, so that means that this guy here, you don't do this guy, but you do instead the triple integral of the divergence of f, which is 1 plus 1 plus 1. This comes out the triple integral of 3 of this over this thing here, but the triple integral over some volume v gives you the volume of that object, right? This gives me altogether 3 times the volume of a sphere radius 2. Got it? So you could do this in your head. And in fact, many of these you can do in your head, if not all. This one here, what comes to mind here? Green's theorem is the line integration. Could you use Green's theorem here? Yes or no? No, why not? It's a 3D problem, Green's theorem doesn't work with 3D problems, but what works with 3D problems is Stokes' theorem. So Stokes' theorem might be able to do this here, and that says if the C is the boundary of a surface, yes it is. So this is the boundary of a surface. I forgot to say the words here that it's, oh no, I did say this. Oriented counterclockwise, so everything is properly, I will not mess you up by orienting this the other way. So everything will always be positively oriented, just nice, so that you can apply this Stokes' theorem here. So Stokes' theorem says that this FDR gives you what? Stokes' theorem says that the integral, oh no, one integration of FDR is equal to what? Double integration over the surface that has this curve C as its boundary of what? Yes, got it. So you got to work out the curl of this F. So this vector field F is the vector field, what is it? Z squared X squared Y squared? So the curl of f is, again, of course, you use Wolfram alpha for this. Curl of, what was it, x squared, z squared, y squared? X squared, comma, z squared, comma, y squared. I think that's right, isn't it? What is it? I have z squared x squared y squared. Okay, my bad. Z squared x squared y squared. So this is a y. This is an x here. What if it was conservative? What would come out now? 0, which means the integral would be 0 because c is a closed curve, but that's okay because this automatically works out. Just as Green's theorem automatically comes out to be 0 if our vector field is conservative, Stokes' theorem is the same thing. So when Stokes' theorem applies, you can just apply it, and you don't have to worry about thinking whether it's conservative or not, because it takes care of it automatically. This is not 0, it comes out 2y, 2z, 2x, 2y, 2z, 2x. This is therefore equal to 2y, 2z, 2x, and now you have to work out this thing here by saying that what happens here if you do this, you multiply, you dot this with minus fx, minus f1 in the dA. Clear? So now you have to figure out what the fx is, what the function z is, but that's easy enough here. In this case, you have to where am I? Where was I? E. No, which one was this? E, right? E. So there's my surface, so the fx is equal to minus 2y, the fx is minus 2x, the fy is minus 2y. You plug everything in and you get the answer. You do have to draw a picture here, because what's the picture that you have to draw here? What do you need why do you need to draw a picture here? Because what's still missing here? So the fx and the fy, you can figure that out, right? Does that make sense? The z you replace by f of x. The d is the one in question. The d is the thing to figure out. So you have to draw this, at least sketch it. What is the d? The d is equal to this is a paraboloid here. And you figure out the d by setting z equal to 0, right? Z is equal to 0 gives you your d. So if z is equal to 0, that means 4 is equal to x squared plus y squared, bringing these to the other side, which is a circle radius 2. So the d is the disk radius 2. This way, which means that what are you going to do to integrate this? Polar coordinates, right? And then once you have written that up, you write this in polar coordinates, and then you do it with Wolfram alpha. Got it? So I want to see this picture here. This picture here. Like this, and then I want to have this written up as double integral of r cosine of theta and r sine of theta. Whatever this works out with the dot product here, with the dot product, some plus or minus here. That's right. So the theta goes from 0 to 2 pi, because you go in full circle here in the xy plane, from 0 to 2. Right. So this is not right here, but whatever comes out here, as when you dot product this and replace x by r times cosine t, and y by r times sine of theta, replace that, and then that works out. Got it? So after this, it's okay to give me It's a straight up answer. But without seeing this here, without seeing this and without seeing this that you convert to protocol, I would be hard pressed to believe that you got this by yourself. Got it? Okay, so we've come a long way, guys. Make me proud, guys. Make me proud on Friday. Okay.